Hi everybody, welcome once again to Burley's World of Physics. Hi children, I am sure that most of you are interested in listening to nursery rhymes. Today in this video, I am going to tell you a story by singing a good nursery rhyme. Well, then you may ask me, what is the connection between a nursery rhyme and physics? Well, watch this video till the end and then you tell me what is the connection. Okay? Well, let us begin. There was a tree, Newton, and his laws of motion. Once upon a time, there was a tree, the prettiest tree that you ever did see. The tree was in a valley and the green grass grew, and the green grass grew all around. There was a house, the prettiest house that you ever did see. The house was near the tree. The tree was in a valley and the green grass grew, and the green grass grew all around. There was a Newton. He was a scientist, the greatest of all that you ever did see. Newton was staying in that house which was near the tree, and the tree in the valley, and the green grass grew, and the green grass grew all around. And in that house there was the floor, the cleanest floor that you ever did see. The floor was in that house where Newton lived. The house was near the tree, and the tree in the valley, and the green grass grew, and the green grass grew all around. And on that floor there was a ball, the cutest ball that you ever did see, resting on that floor, which was in the house where Newton lived. The floor in the house, and the house near the tree, and the tree in the valley, and the green grass grew, and the green grass grew all around. Then there was this boy, the naughtiest boy that you ever did see. He was playing in that ground near the house where Newton stayed, the house near the tree, and the tree in the valley, and the green grass grew, and the green grass grew all around. The ball was there, always at rest, lying on that floor, till one day in came that boy, and he kicked the ball with all his might, and swish went the ball up from the floor and out of the door in that house, and the house near the tree, and the tree in the valley, and the green grass grew, and the green grass grew all around. Newton saw the ball hour after hour, day in and day out, lying on that floor, always at rest on that floor, in that house, and the house near the tree, and the tree in the valley, and the green grass grew, and the green grass grew all around. Newton started thinking, why did the ball remain on that floor when left alone, and why did the ball move when it was kicked? And out came from Newton the laws of motion, inertia, force, and acceleration. F equals ma. So, this was the story, the truest story of all the times on Newton and his laws, and the boy and the ball, and the ball on the floor, and the floor in the house, and the house near the tree, and the tree in the valley, and the green grass grew, and the green grass grew all around. And the green grass grew, and the green grass grew, and the green grass grew all around. Newton's laws of motion are universal laws obeyed by all material objects on the earth as well as almost all heavenly bodies. These are usually stated in the following way. 1. A body will continue in its state of rest or of uniform motion in a straight line unless acted upon by an external force. That means no force means the body will be at rest and its speed is 0. In the presence of an applied force, uniform motion results, that means speed is greater than 0. Thus, the first law introduces the concept of force. A force is an external interaction or influence applied on a body that tends to change the state of rest or of uniform motion in a straight line. A force thus will change either the magnitude of the speed of the body or its direction of motion or both. So once again, no force, the body is at rest, that means speed is 0, and in the presence of an applied force, uniform motion results and the speed will be greater than 0. Here the effect of the force is to change the initial speed u is equal to 0, that means at rest, to a finite speed v greater than 0. In the case of the earth revolving around the sun's force of attraction changes the direction of earth's motion and the magnitude of the rotational speed to a less extent. In this context, we have to be a little more careful about our wordings. When a body continues in its present state of rest or of uniform motion in a straight line, it does not always imply that there is no force acting on it at all. It may also be the case that there are more than one force acting on it in such a way that the net force is 0. So a pair of equal and opposite forces can result in a net or resultant force equal to 0 when these are applied in opposite directions. Such a combination of forces whose resultant is 0 is called balanced forces. Now, velocity is a vector quantity, meaning thereby that it has both magnitude and direction. The magnitude is the speed and the direction is the direction of motion of the body. The rate of change of velocity consequent on the application of an external force is an important physical quantity. It is referred to as the acceleration. Newton's first law also throws light on an important property of any material object. This is called inertia. Inertia refers to the inherent reluctance of the body to respond to a change in its state of rest or of uniform motion in a straight line consequent on the application of an external force. Physically, inertia is a passive property of matter that quantifies how much a body resists changes in its state of motion. Mass is the quantitative measure of that resistance. Now, Newton's second law is a quantitative statement for the acceleration resulting from a force applied on an object of mass m. It affirms a direct proportionality between the applied force and acceleration, the proportionality constant being the mass m. That means F equals ma. So that means the acceleration is proportional to the force. So if there is more force, there is more acceleration, and vice versa. Also, if F is equal to 0, then A is equal to 0, which means the velocity is a constant. Thus, a statement of the second law is the effect of an applied force on a body is to impart an acceleration on the body in the direction of the force and proportional to the magnitude of the force. Again, F is equal to ma implies that if there is no applied force, that means F is equal to 0, A is equal to 0, hence the speed remains a constant. So a body at rest will remain at rest, and a body moving uniformly or V is a constant in a straight line will continue its uniform motion along the straight line. So we are back to the first law. So we can say that the first law is a special case of the second law. Now coming to the third law, which deals with the ideas of action and reaction. Now these constitute a pair of equal and opposite forces, like F1 and F2 shown here, which are in opposite direction and their magnitudes are equal. The naming is relative. If F1 is the action, F2 is the reaction, and vice versa. So the Newton's third law is stated as follows. For every action, there is an equal and opposite reaction. But remember, these forces act on different bodies, so they won't cancel each other. Let us look at the ball on the floor in our nursery rhyme again. The ball is at rest on the floor. It means there is no net unbalanced force acting on the ball. Here the main force acting on the ball is its weight, mg. That is the gravitational pull of the earth acting downward. Since the ball does not move, there should be a balancing force equal but acting in the upward direction. This is the so-called normal reaction on the floor on the ball. The ball acts on the floor with a force equal to its weight. This is the action force. The reaction force is provided by the normal reaction of the floor on the ball. It should be remembered that Newton's laws are an excellent classical approximation, but they are not exact in regimes where relativistic or quantum effects become important. Well, that's all for today. I'll be back soon with more interesting videos explaining some basic physics principles. Till then, goodbye.